Yep.
In this lab, we will be looking at identical particles. There are two kinds of particles in the universe. Those with fraction spin angular momentum, known as fermions, and those with integer spin angular momentum, known as bosons. Because both protons and electrons are fermions, the behavior between these particles as a result of their spin angular momentum has significant consequences for all atoms and molecules. Identical particles cannot be distinguished and cannot be described in any way that suggests that they are indistinguishable. Therefore, we cannot distinguish between the two electrons, or fermions, in the following experiment. The wave function for the two electrons is phi of x sub 1 and x sub 2 equals phi sub 1 of x sub 1 times phi sub 2 of x sub 2 minus phi sub 1 of x sub 2 times phi sub 2 of x sub 1.
The first question we looked at are, what are the two general features shown by the following three equations with our wave function psi of x1, x2? The first property we looked at was the anti-symmetry of the wave function, and the second property we looked at is that as the limit as x2 approaches x1, essentially that as one particle approaches another, that they cannot occupy the same space. That the actual probability that they will exist in the same space is 0. The proof of that is shown here in the equation 3. So the limit of our function as x2 approaches x1 is shown by this equation. In order to evaluate that, you plug in x1 in all of the x2 positions. So here we have an x2, then we have an x1, here x2, there an x1. These equations are equivalent and therefore equal 0. Therefore the limit of our function psi x1 of x2 as x2 approaches x1 equals 0.
In order to determine if our wave function is antisymmetric, we substituted in each particle into the original one's location, as seen right here. So, subbing in the particles for the opposite position, we evaluated the wave function to see if it was indeed the negative wave function with the particles substituted in the opposite position. So we substituted in the particles into our original wave function. We moved this term to the left and then factored out a negative value, and we indeed get back to our original wave function. Therefore, our wave function is antisymmetric. So the takeaways from question 1 are particles cannot occupy the same space with the same spin, and the wave function is antisymmetric.
The second question in our lab asked us to normalize our wave function. This first equation right here is the general form equation for normalizing any wave function. It's the complex conjugate of the wave function times itself. And we have to do a double integral in this case because there are two particles, so there's two variables here. What we want to solve for is this constant n sub c, and it's also squared because of the two variables here. Right here, we plug in our actual wave function, our psi sub x1, x2, and that's seen right here. Because there's no imaginary aspect of our function, we simply square it, as seen up here. Right down here, we have the entire expansion of that square, of that binomial. These two inner terms right here are going to cancel out because the two terms boxed in red, this psi n sub 1 x sub 2 and psi n sub 2 x sub 2, since they're with regards to the same particle, they both cancel out, according to this equation here, because you take the integral of the two separate functions and they are 0. So this term becomes 0 and this whole term falls out. The same is true for this term right here, because we have again a psi n sub 1 x sub 2, psi n sub 2 x sub 2. It does the exact same thing. The two outer terms are squared and they simplify to this equation down here. These are each separate integrals, but they're with the same wave function, and so they equal 1. So this ends up being 1 times 1 is 1, 1 times 1 is 1, and then down here we get our constant n sub c equals 1 over the square root of 2. In more general situations, the constant will be 1 over the square root of n factorial, where n is the number of particles in your system.
So, in order to calculate the average location of each particle, the double integral of the wave function had to be taken with respect to each particle. So we took the double integral of each function within our defined area of our one-dimensional box with respect to each particle. And we found that in taking the double integral with respect to each particle, we found that the particle's average location was in the center of our defined box, or L over 2 for each. The reason for this is, since there's no potential within the box and there are no repulsive or attractive forces, each of the particles' average location will be in the center of the defined box. When we graph the two particles within the same location, from our plot you can see that one particle has a positive charge or a positive spin, and the other particle has a negative spin. The reason for this is, as we showed in our first problem, two particles cannot occupy the same location with the same spin. Therefore, when two particles are located within the same location, they have an opposite spin. This proves Pauli's exclusion principle.
The sixth question we were asked was, will the Slater determinant vanish if both of the electrons have the same spin function? We can see right here in this equation, this is our wave function basically in matrix form. This right here is the Slater determinant, and we want to look and see if this determinant equals 0 if each particle, that is x1 and x2, have the same spin function. That is, they're either all alpha or all beta. For our purposes here, we chose all alpha. It doesn't really matter. This is just a show. So to determine the determinant, it is this function times this function minus this function times this function. For our purposes, we canceled out. We didn't cancel out. We omitted the alpha spin functions to simplify it, and essentially, this term minus this term does not equal 0, and so the Slater determinant will not be 0 because the particles are in two different energy states. The energy states are denoted by the n sub 1 and the n sub 2. So here we have the first particle, x sub 1, is in this first energy state, and over here the x sub 1 particle is in the second energy state. The energy states aren't necessarily 1 and 2. These functions just denote different energy states. And so the determinant won't be 0 for particles with the same spin. The takeaway from this problem is that two particles can have the same spin if they are in different locations and energy levels.
In order to evaluate if the Slater determinant will vanish if both electrons have the same spin or same location with different spins, we had to evaluate the Slater determinant, and we determined that it will not vanish. So the significance of this is that since it does not vanish, it means that they can occupy the same location with different spins, which it basically proves Pauli's exclusion principle, that in order to be in the same location, they have to have different spins.
In order to determine if the ground state for the two-electron system and the first excited state are orthogonal, we first had to define two wave functions. The first wave function for the ground state was defined with the principal quantum number n1 equals 1 and n2 equals 2. The first excited state wave function was defined with n1 equals 1 and n2 equals 3 for the quantum numbers. In order to see if the two wave functions are orthogonal, we took the double integral with length equals 1 of the ground state wave function multiplied by the first excited state wave function and evaluated that to see that it equals 0, which proves that it is orthogonal.
Next, we're going to look at a three-particle system, and we're going to use the Slater determinant to show anti-symmetry with these wave functions. So we chose to use the Slater determinant because writing out in long form the equation for 3 electrons takes forever. Basically, what we're going to show is that you can move one of these columns, you can exchange their places, and the function will be equal to the negative of itself. Earlier we showed it with the 2-particle system, and this is just how you would do it with the 3. So in order to prove this, we're going to look at mathematical determinant rules and simplify the determinants instead of using all the symbols above. So the matrix we're going to use is a 2, 1, 1, 2, and what we're basically showing here with this equation is that if you move this column, this 1, 2 column, over to the left, and you exchange it with the 2, 1 column, that it will equal 0. Essentially that they are opposite. And so here we have all the math worked out, and they are indeed opposites of each other. So we have our first matrix, it's equal to 3. We have our exchanged matrix, it's equal to -3. Therefore, our exchanged matrix is equal to the negative of our first. And because over here, we showed that these two are actually equal because they equal 0, we can say that our first matrix is equal to the negative of itself. And so we've proven anti-symmetry. And we can use these same basic determinant rules in our system up here. So we can exchange this column of functions for this column of functions and end up with a function that is equal to the opposite of itself.
The next question we investigated was, what is the ground state energy in quantum numbers in the 1D box for a 3-electron system? First, we defined the ground state principal quantum numbers for the 3 electrons. N1 equals 1, N2 equals 1, and N3 equals 2. Then we showed the energy function for the electron. Notice the terms surrounded in blue we're factoring out as a constant and dealing with just the principal quantum number. This equation here shows that the energies are additive, so the total energy of the 3 electrons in a 1D box is the energy of the first electron plus the energy of the second electron plus the energy of the third electron. When we substitute the 3 quantum numbers into this function, we get a constant of 1 squared plus 1 squared plus 2 squared, which simplifies down to 6 times the constant, which would be the total energy of the 3-electron system in a 1D box.
Finally, we were asked, what is Fermi energy? It is the energy of the highest occupied quantum state in the system of fermions at absolute 0 temperature. Essentially, this means that even at absolute 0, there is movement of particles, and that everything is always moving. Nothing is completely stationary in real systems. The second question is, what is an ideal Fermi gas? It is a physical model assuming a collection of non-interacting fermions. Essentially, it is the quantum mechanical version of an ideal gas. finally, we were asked to look at the nuclear spin states of several different isotopes. First, we have hydrogen. It's 1/2. Second, we have deuterium. It is +1. Thirdly, we have 3 helium. It's +1/2. Then we have 4 helium. Its nuclear spin is 0. 6 lithium has a +1 spin. 7 lithium has a -3/2 spin. 23 sodium has a +3/2 spin. 14 nitrogen has a +1 spin. And finally, 19 fluorine has a +1/2 spin. Here's our work cited.
Brought to you by the PChem Warriors. And remember everybody, operators must always operate on a function.